Chapter 14 is on equilibrium. So far in this course, we've been focusing on reactants and products, but not really talked about what happens if a reaction only goes part way. So equilibrium is the state where some of the reactants have gone to products, but the reaction also goes backwards. The products are also being converted back to reactants. And for many reactions, the rate of the forward reaction and the reverse reaction end up at a point of equilibrium where you don't go 100% to the products, you end up somewhere in the middle. So here's an example. If we look at this simple reaction of A going to B, we have a forward rate of 0.15 per second. You can see that at some point here we run out of A and everything has converted back over to B. But what happens if we add in a reverse reaction where our B is also being slowly converted back over to A? So we've set a reverse K value of 0.05 per second. So it's happening slower than the forward reaction, but still happening. What happens when we combine those two? What we get is an equilibrium reaction, where our forward reaction is still happening at 0.15 per second. Our reverse reaction is happening at 0.05 per second. And after 30 seconds, we achieve equilibrium, where our concentration of A is steady at 0.025 molar. Our concentration of B is steady at 0.075 molar. But if you look in at the atomic scale, both reactions are still happening. It's just that our concentrations of our reactants and products are steady. So dynamic equilibrium, we still have some reaction going in both directions, but we don't see an overall change in concentration. So this is what I just said. As the forward reaction slows down, you run out of your reactant, and the reverse reaction accelerates. You have more product, so it can go back to reactant faster. Eventually, they're going to reach the same rate, which is called dynamic equilibrium. The rates of the forward and reverse reactions are equal. That does not mean that the concentrations are equal, because the rate constants might be different. So once you reach equilibrium, your concentrations are going to remain constant because they're being consumed and made at the same rate. So the concentrations of reactants and products are not going to be equal at equilibrium, but there is a relationship. That relationship is called the law of mass action. And what we can see for our generic reaction here, some coefficient times A plus some coefficient times B is in equilibrium with some coefficient times C plus some coefficient times D. We get this equation out of it. K, capital K, our equilibrium constant, is our products raised to their coefficients divided by our reactants raised to their coefficients. And we're going to get lots of practice with writing K's, because we're going to use them extensively in chapters 14, 15, and 16. And we'll also use them a little bit more in the later chapters as well. Now, it is essential, I cannot emphasize this enough, do not mix up capital K, the equilibrium constant, with lowercase k, the rate constant. Remember, the equilibrium constant, like we just learned, you do raise the concentrations to the power of the coefficients. But when we're talking about rates, like we did in the last chapter, unless you're looking at a mechanism with elementary steps, you cannot get the order of reaction from the coefficients. Those are not the same. In equilibrium, we do use the coefficients. So do whatever you need to do to get that straight in your head, because I see that mixed up all the time. Okay, so moving on, talking about K. Writing equilibrium constants. Here's our generic one again. Let's look at a specific example. So here 2 N2O5 is in equilibrium with 4 NO2s and 1 oxygen. So our equilibrium expression is our concentration of our products. So NO2 raised to their coefficients, 4 times oxygen raised to its coefficient, which is a 1, so we don't necessarily write it, divided by our reactants, N2O5 raised to its coefficient of 2. So overall, our K is our products raised to their coefficients divided by our reactant raised to its coefficient. Now, the size of your equilibrium constant can tell you something about which direction the equilibrium lies. So if you have a large equilibrium constant, that means that you have a lot of product over a small amount of reactant. A big number divided by a small number is going to be a large number. That tells us that our equilibrium lies to the product side. Similarly, if we have a small equilibrium constant, that means that we have a small number on the top, our nitrogen monoxide, divided by a large number on the bottom for our nitrogen and oxygen. And so then we get an overall small number telling us that our equilibrium lies far to the left, to the reactant side. Okay, we have some rules for writing equilibrium expressions that we're going to go through, and then we will practice with them. So the rules for writing equilibrium expressions. Rule number 1. Write the equilibrium expression for the chemical reaction as stated. That means do not, for some reason, flip around your products and reactants that's going to affect your equilibrium constant. So write it for the reaction that you are given. You're going to multiply your product concentrations, divide by the product of the reactant concentration, so it's our products over our reactants. And then the stoichiometric coefficients become exponents, so p to the small p, r to the small r. So coefficients become exponents. Number 4, only calculate for the common phase. That means if you have A that's aqueous plus B that's a solid is in equilibrium with C that's aqueous plus D that's aqueous, you're going to ignore the solid. So the common phase is typically either aqueous or gas phase. And if you see something that's a solid or a liquid, you can ignore it in the equilibrium. In fact, you should ignore it in the equilibrium expression. Speaking of gases, if you're using a gas phase reaction, you can use the partial pressures instead of concentrations. Then we often use the subscript P to indicate that it's an equilibrium constant using pressures instead of the concentration, which we either use a KEQ or a KC. If you want to convert between a pressure and a concentration K value, you can use this equation, Kp equals Kc times RT to the delta N. R is the gas constant, T is the temperature the reaction is taking place at, and delta N is the change in stoichiometric coefficients from reactants to products. We will look at an example of that using this equation later on. All right, our next rules deal with what if you are, say, adding reactions together using Hess's law. What do we do with our K values? If you're reversing the reaction, you need to invert KEQ, which should make sense because we're products over reactants. If we reverse the two, then we need our old reactants over our old products, so we're going to invert our KEQ. If you multiply stoichiometric coefficients by a number, raise the equilibrium constant to the power of that number. So if you had one equilibrium with 2 and you multiplied all this by 2, that's going to make your new coefficients 4, 2, and 4. To change your KEQ, you can just take KEQ to the second power, and that will double all those individual coefficients in your equation. And then if you add two reactions together, you multiply the equilibrium expressions. So with delta H, we added them together. With KEQ, we're going to multiply them. All right, so let's work through a couple of questions using our equilibrium expression. This question says, write the equilibrium constant expressions K and predict the position of equilibrium for the following. So 2 sulfur dioxide plus oxygen goes to 2 sulfur trioxide. And we have a K value of 8 times 10 to the 25th. So our K is going to be our product concentration, SO3, raised to its coefficient 2, divided by our reactants, so SO2 to the second power times our O2 to the first power. We could also use partial pressures because everything's in the gas phase. A large K value, remember, means that our equilibrium lies to the product side. Now let's look at our second reaction. Nitrogen plus 2 oxygen goes to 2 nitrogen dioxide with a K value of 3 times 10 to the minus 17. We can write our equilibrium expression, our concentration of NO2 squared divided by our concentration of nitrogen times our concentration of oxygen squared. And this time our equilibrium lies to the reactant side because of that small value of K. All right, another question. When the reaction A is in equilibrium with 2B, reaches equilibrium, concentration of A is 1 times 10 to the negative 5th molar, B is 4 times 10 to the negative 1st molar. When the reaction 2B is in equilibrium with Z, reaches equilibrium, B is 4 times 10 to the negative 3rd molar, Z is 2 times 10 to the negative 6th molar. Calculate the equilibrium constant for each of these reactions and the equilibrium constant for the reaction 3Z is in equilibrium with 3A. Okay, so our first reaction, our K is going to be the concentration of B squared divided by the concentration of A. We can plug in our numbers. So we're going to get 4 times 10 to the negative 1st squared divided by 1 times 10 to the negative 5th. And I can do that math. And I get an answer of 1.6 times 10 to the 4th. For my second reaction, my equilibrium constant is going to be Z, concentration of Z, over the concentration of B squared. So there's my second reaction. And in this case, this squared is outside. My concentration of Z is 2 times 10 to the negative 6th. And my concentration of B is 4 times 10 to the negative 3rd, and that gets squared. So my K value for my second reaction is 1.25 times 10 to the negative 1st. And then it says calculate the equilibrium constant for the reaction 3Z goes to 3A. So hang on, my first reaction, this is for A, equilibrium with 2b. Then my second reaction is 2b in equilibrium with z. Now for both of these, I want A as a reactant, so I'm going to reverse and multiply by 3 for both of my equations there. So when I reverse it, I'm going to get 2b in equilibrium with A, then I'm multiplying by 3. So for my K, it's going to be 1 over 1.6 times 10 to the 4th, and then that's going to be cubed. And then for my second reaction, again, I'm multiplying by 3 and then reversing it. So for my K, it's going to be 1 over 1.25 times 10 to the negative 1st and cubed. Let me do those math problems a second. So for my first one, I get 2.44 times 10 to the negative 13th. For my second, I get 5.12 times 10 to the 2nd. And then I'm going to multiply those together to get my final K value of 1.25 times 10 to the negative 10th.